Patty and myself are the program chairs of ICSE 2013, and as if you agree to be program co-chairs of ICSE, you know 10 years later there is another job to do. And as David has already said, the most influential paper award of ICSE, I think, is one of the most well-established awards of conferences. And the way it works, I will describe in 1 minute, not more. You select a committee. This was our committee. And before I go further, I want to thank the people who contributed to that. Because believe it or not, selecting the most influential paper out of around 80, 90 accepted papers is not so easy job. I put a few bullets, and Betty and myself put a few bullets about the selection process. You can read, I'm not going to explain. The main thing about it, in my point of view, is that the selection was really a common sense. So there wasn't any discussion. This year we were really lucky. It was extremely clear which was the most influential paper of ICSE 2013. And the winner is?
And the winner is SemFix, a program repair via semantic analysis by Ditien Nguyen, Dichu, Abhik Roychoudhury, and Satish Sandra. And so this paper was really looking at symbolic analysis techniques to support automatic program repair, and it really led to a new direction to how using symbolic execution for specification inference. And we're very happy that 2 of the 4 authors are actually able here to come join us to accept this award. So please come.
Okay, good afternoon. Can you hear me? Okay, thank you very much to the committee for judging our paper worthy for this very prestigious, most influential paper award. We are very honored. I'm Abhik Roychoudhury from the National University of Singapore, and I will also be joined in this talk later on by my co-author, Satish Chandra. So this paper, as was mentioned, was the SemFix paper, the program repair by semantic analysis. It was co-authored by 2 other student authors who are currently not in academia, but they are doing well. So when I informed them, one of them told me, well, I'm now the CTO of a scale-up, not a startup, but a scale-up in Shenzhen, China, and we are doing static analysis and security testing, and I'm now employing 110 people. So even though they are not in academia, this is certainly a good moment of pride to also celebrate their achievements. So let's talk about program repair, which is what this paper is about. In program repair, you have a buggy program and some correctness specification, and the correctness specifications, usually the setup that I'm talking about is in the form of test cases, and then you produce a patched program. The applications of program repair are myriad. For example, it can be in education. Let me try to use the laser pointer here. It can be in education. So this is something we have our own homegrown system at the National University of Singapore, for example, where we teach software engineering in the form you would teach operating systems. So we give out a base intelligent programming, intelligent tutoring system, and then every year the students do projects, and then this intelligent tutoring system gets deployed in the first year programming courses. So it's really a real life setup where the teaching of the software engineering project is a real life software engineering project, and this is for giving feedback as well as automated grading to students, and the core of this system is really program repair. So all of the techniques that I will be covering today really form the core of this system. It is used quite a bit for, of course, for correctness, for improving developer productivity, and it's used quite a bit for security vulnerability repair. So in fact, we have, and several others, not just our group, but many other groups have used it for security vulnerability repair, because the exposure of the software systems to security vulnerabilities is large if you don't go for automated repair. It can easily take months. So to give a retrospective of how we started coming into this idea, just a little bit of it. So before working on repair, at least I was working on the debugging problem. And both the debugging problem and the repair problem, the core of the problem really comes from the lack of specifications, because oftentimes you don't have very good specifications to work with. So if you don't have any formal specification and yet you are stuck with a software system which you somehow have to root cause the errors or fix the errors, then what do? So on the right-hand side of this slide, you actually see this view graph. This is from my talk in FSC 2010 in New Mexico, so about 13 years ago, where we actually used symbolic execution for debugging, where we compared the embedded Linux, the BusyBox embedded Linux with the GNU core utils, and actually used that to root cause many crashing errors. And we were extremely happy and extremely proud, but the thing is, oftentimes you don't have a reference implementation like this. So this is really what led us to this idea that instead of depending on reference implementations, how about tests? And can you extract really use symbolic analysis to extract specifications from tests and use that to guide the repair? So this is really the first time we presented the paper. Actually, this was presented prior to ICSE in a Darkstuhl seminar in February 2013. You see many familiar faces here, and if you want a spot the author contest, we are right here in the middle of this picture. So the main idea was to use repair by exploiting symbolic execution technology, because you really have test cases. Tests are incomplete specifications, we all know. So you want some generalization capability from the tests. So we are using symbolic execution to do that generalization. And what this comes as a very big advantage is that this gives us scalability not just with respect to the program size, but scalability with respect to the search space size, which is very important in repair, because you might have to consider many edits. We in fact do repair via constraint solving, and we do not depend on any formal specifications being available. Here's a very simple example, which I will go through quickly. So this is intuitively obvious. We all know what a triangle is. It takes in the three sides of a triangle and returns the kind of triangle. So in this case, there are several bugs in this program, but the definition of the isosceles triangle is incorrect. And we have a typical test suite that is given: 1 for an equilateral triangle, 3 for the three possibilities in an isosceles triangle, and 1 for a scalene triangle. So in this philosophy of generating specifications for tests, what you will do is very different from the way symbolic execution is normally used. So you would actually do concrete execution of the tests and not symbolic execution, but somewhere down in the middle where you want to fix the error, which is essentially an unknown expression, you will convert it into an unknown function and infer some tiny properties about this function. So for example, for this test 2, 2, and 3, it will infer the property that I don't know anything about this function f that needs to be inserted here for the isosceles triangle, but it should at least return true for 2, 2, and 3. And if you capture enough of these tiny properties over enough number of test cases, you can use like a synthesis engine or even a search engine in the back end to generate the appropriate expression. And of course, this can be scaled up to multiple line fixes as well. So symbolic execution, I will comment a little bit about symbolic execution. Symbolic execution is a very established technology. It was first proposed in 1976 in this paper, Symbolic Execution and Program Testing, which appeared in Communications of the ACM. And since then, tremendous amount of advancements have been done, a lot of wonderful research on using symbolic execution for testing and verification. I would like to take a moment to highlight that the use of symbolic execution that we have is really very different. We do not have any execution with symbolic variables representing the input variables. The only symbolic variables are the patch variables, and essentially this would be a higher order reasoning. This would be at least a second order reasoning because it is an unknown function, but we are converting it into first order reasoning. We are introducing this variable x and getting properties about this variable x. So here I'm just showing how the symbolic execution for testing for this program will proceed. You would have essentially for each of the parts in the program, you would have a leaf node. And the important point is the symbolic variables A, B, and C. These are really the input variables. So here in this view graph, you can actually see the two sides, so to say. So on the left-hand side, you see the symbolic execution being used for repair. So where actually I'm feeding in concrete test cases, and then I'm getting some properties in terms of the symbolic variables that represent the patch variables. On the right-hand side, you see the test generation, where really speaking, the only symbolic variables are the input variables. So in summary, just to kind of summarize this portion of the work, so we would like to place our work with respect to other works in program repair that have taken place. So there are works on search-based repair. Our work essentially started off this domain, I would say, on semantic repair, where instead of doing an explicit search over the space of patch candidates, you really try to get a constraint that represents all the possible patch candidates that would pass these test cases and also other similar tests by generalization. And then you would try to synthesize code via constraint solving at the back end. There are also other kinds of works on learning-based repair that have happened in the meanwhile, which essentially try to prioritize the patches. So in terms of a schematic, we would consider this schematic where essentially we go through the tests, generate a repair constraint, and then consider the conjunction of all of these repair constraints for the purpose of guiding the synthesis or the search in the back end. The important point with respect to this particular contribution is that we want to address the issue of patch overfitting. In the program repair community, this is something which is considered very, very important because you have essentially test cases, and from the test cases, you would like to generate patches which do not overfit the test data. So this way of generating the constraint and then trying to solve the constraint to guide the patch generation process provides a very nice solution to the patch overfitting. My co-author was supposed to take over from here. Yeah, Satish. Yeah.
Thanks, Abhik. All right, thanks, Abhik. So SemFix was 2013, and we thought that it would be a good idea to briefly see what has happened in this domain since then. So one of the things I think all of us will agree on, major change that has happened in our field, in our community, is machine learning making significant inroads in the space of software tools. And I think, the two main reasons is that there is a lot of code out there to train on, including code versions and whatnot, and there has been tremendous progress in the space of machine learning itself, especially deep learning and all the compute power that we have available today. In any case, this has sort of revolutionized the field to some extent, and we had several talks already at the conference about code completion, but in addition, we have used machine learning for code search, for troubleshooting, and of course, for automated program repair, as Abhik already mentioned. And one of the things that I find fascinating is that the impact of machine learning in our field went from sort of research to mainstream very, very quickly. Now let's talk about a little bit about how machine learning comes to automated program repair. I see the ED is in smaller font. That's a candidate for repair, it seems. So when we think about program repair, the data that you have is actually the corpus not of code, but of code changes. So if you preserve every revision, every commit version of the code, not just you, everyone else has deposited on in code repositories, you can actually mine those changes out, and that become your training data, because that's a wonderful source of edits. It's a distribution of edits that people have made in the past. Sometimes you also know which bug symptoms those edits were about, but it's not necessary to always know that even. And so once you have this distribution of edits, then the machine learning problem is given the context of a buggy code fragment, what edit do you want to predict? And from that point, the story becomes sort of similar to how we have done program repair without machine learning, in the sense that we still tend to have to localize the error as before. Instead of doing a search-based or a semantics-based technique here, we would predict an edit. That's different. And then you still have to validate whether the patch that you applied is in fact the correct patch under a certain definition of correctness. And the picture on this visual essentially just simply focuses, look at the right side picture here. So we are using learning-based repair methodology in addition to fault localization and all of that. The patch verification is not shown in this picture. So I would like to take a few minutes to speak of two industrial, I work in industry. I would like to speak of two industrial projects or projects done in industry relating to program repair. The first one was work that my team and I did at Meta. This work is called GetAFix. This is about 2019. And here the observation is that if you are looking at version history and if you're looking at errors reported by, let's say, another tool such as a static analysis tool, you know between these version saves whether new warnings were added, that's in green, or whether warnings went away, that's in red. So when warnings go away, it could be because you fixed the warning, or maybe the code that had the warning was deleted for whatever reason. But let's assume that we are fixing warnings. And so if you have a large number of these saved over millions and millions of version changes, you can formulate, you can collect pretty good training data for what it takes to fix these kinds of bugs. So for a very quick example, what am I doing here that's not, okay. So for a very quick example, you can think of this simple fix, in air quotes, of a null pointer error where someone wrapped this call to a method in a null check. Okay, so this is a kind of a fix. And now what GetAFix does is look at large number of these kinds of fixes and organizes them in a tree of patterns. And it's a very natural operation using anti-unification. And once you have this tree of patterns, then the remaining problem is that given a new context, how do you predict which patch to apply? And we do that using probabilistic ranking. More details are in the paper mentioned here. So I would like to step back and share what we really learned from doing one of these projects. So one very interesting and surprising thing to us is that developers are really picky about their code. Even if you come up with a semantically equivalent fix of code, it's not necessary that developers will accept it. So here, GetAFix resulted in about 40% of fix suggestions accepted, but there is a 9% box that you see semantically equivalent fix. These were fixes that any reasonable person would call correct, but developers don't call correct because they insist on exactly the way they want to fix the program. So that was a very interesting. Second thing is that a lot of techniques in this space do assume that we can try things multiple times. So you generate a patch, you recompile your system, and then you rerun the test and so on. In our context, this was not really an option because of compute budget reasons. And so we had to work very hard on getting just a top-ranked patch and hope that this works. So this may be a lesson for some folks. And then finally, convenient UI integration is super important. Otherwise, the impact of the tool is not realized. So here, for example, I'm showing you a screenshot from the code review system where whenever a static analysis tool reported a problem, GetAFix inserted a suggested patch with options of, hey, do you want to reject this or accept this? And just a very simple UI idea, but this was important in getting suggestions landed, which is good for metrics and whatnot. I would also, I work at Google now. I would also like to mention work that my colleagues at Google has done. This work predates my being at Google, but the idea is in a way similar. This work looks at fixing build errors or compile errors. Again, using similar ideas, you can look at the history of code edits that were instrumental in fixing these kinds of errors. And this technique used neural machine translation to actually generate the fix. The screen shots at the bottom show an example of, you see this red squiggly arrow. That is a occurrence of a compiler warning or compiler error, and the right-hand side is the corrected code. Again, UI-wise, it was very useful to sneak in just a little bit of hint as to where a machine-generated fix may be hiding, so you can click, observe it, and land the fix. Okay, so enough about those projects. Let's step back and see where are the challenges in this field, where ML has helped and so on. So in our view, ML has really helped in generalization of fixed patterns, interpolation between patterns and so forth. So we already saw many talks that were talking about the differences between templates and neural prediction and so forth. This is where machine learning based techniques have really shown their mettle. The other place where they have ML has helped is, or rather has made a lot of impact, is being productive in fixing static analysis errors and compile errors and things. So narrow domain specification of what needs to be done is easier, but these are places where machine learning has really helped, helped us win. We see continued challenges in the field. Patch accuracy is a problem because tests may not capture the full spec. Patches may be complicated. They may be distributed across many lines or across many functions, the so-called multi-hunk repair problem and so on. Localization continues to be a challenge because you may not actually even know where to make those changes. Nevertheless, what is cool is that within this community, we looked at the number of correct patches computed for defect4j over the last 5 years, and you see an upward trend. That's the bar chart showing on the right. Plotted from 2019 to 2023. Maybe we got the heights of some bars wrong a little bit, that's okay. But one of the problems here is that we are still about 70 something out of 395. So there is ways to go, but we are making progress. Okay, let me now come to the last thing that Abhik and I want to say. So as it has been clear during this conference in our professional lives that coding is undergoing, the practice of software is undergoing a transformation because of availability of these large language models. In particular, a lot of people are using Copilot to write their code and so on. So with these large language models, they are having a profound impact on our community and on research. So a lot of things can be done pretty much out of the box or with few short prompting, and this is quite impressive and making a change in how things are done. So now the question is that as ML, or let's say, instantiated in tools like Copilot begins to generate more code, what is the continued role of APR methods, program repair methods? So here we have a couple of points to share. One is that just because code is machine ML generated does not mean bugs will not appear. It may be buggy to begin with. Also, if it appears correct, there may be future cases during deployment where conditions might change and a bug might get exposed. So the need for program repair will continue to be there. That said, with we do expect models to stop making routine and more predictable kind of bugs. That will just organically happen because of the way the machine learning technology is progressing. Another interesting point to share with you is that as we are all becoming prompt engineers, it's possible that one day prompts will become the source of truth. And really, when you talk about repair, it's about editing the prompt, and the act of repair may migrate upwards from code to prompt. So we'll see if that happens or not, but that's an interesting thought. With that, I'll hand it back to Abhik to share some thoughts on trust. So Abhik, yeah.
Okay. Yeah, thanks, Satish. So as we move towards more automatically generated code, and we have a combination of automatically generated code and manually written code, the question we feel will remain whether ML-generated code will be considered trusted enough to be integrated into a software project. The analogy I have here is that of a self-driving car. We have been hearing about self-driving cars for very long, but we don't see that many self-driving cars on the road because there are a lot of driving regulations. The software industry is unregulated. So you can kind of write risky code, but the assumption is that the code is written by a person, so you can still somehow get back to that person. So there is some informal assurance. When the code is really written by a machine, then that informal assurance is also gone. So what can we do? So we have only a few minutes, so we just leave all of us with some thoughts maybe. So there is increasing amount of work of programs written from large language models. We had a paper right here in this conference, which was presented today afternoon, of automated repair of those programs from large language models, where probably something like Copilot generates the code and then automated program repair is used to improve the code. Now, as a byproduct of that, something that can be done is that the program repair as a byproduct can also produce evidence that the repaired code is correct. So for example, something like symbolic execution or other technologies can play the role of steering the search. Or here you see a tiny video steering the search over the domain of inputs to generate additional test cases, and also do the specification inference over the domain of patches to reduce the space of patches. And then the oracles or the expected behavior of these additional inputs could come from the natural language descriptions, which are now provided. So this is the last slide that we have, that in the world before this LLMs, we had manually written code. We have a programmer. She is sitting here constantly debugging and maybe fixing issues. Whereas when we have automatically generated code, we can have specifications in natural language. Maybe something like Copilot produces the automatically generated code. But there continues to be a role for the semantic techniques, not just to repair the code, because the repair can be done by other techniques as well, but also as a byproduct of the repair to produce evidence so that you trust it enough to integrate it into your software project. So that's our thought, and with that, with this position on trusted automated programming, we would like to thank you for your attention, thank the committee for this very prestigious award, and also open the floor for questions.
I would like to challenge one of the claims that Satish made. So you said that things are getting better because we are fixing more and more of the defects for J defects correctly. So I would like to contest that claim. Please. Because I think what's possibly happening is we're overfitting more and more to the defects for J benchmark, because that's the only benchmark we're using again and again. And there's been multiple papers, including one in the ICSE, that has shown that actually when you go to a different benchmark, these techniques that perform better on this version of J, even later versions of J, just doesn't generalize. So I'm not convinced that we're doing better. Are you convinced?
Okay, so let me answer it like this. So when I read these papers, and I have been reading these papers over the last several years, it's not, so there is also new ideas. Maybe the fault is that we don't really have a good supply of benchmarks and so on. But when I read these papers, there are fresh ideas. Many times the ideas make intuitive sense to me. And I believe that if we took a paper from 5 years ago and state of the art now, bring a different benchmark, I think the newer papers will do better. So that's how I would like to like to answer that. I think Abhik wants to say something.
Maybe, but having said that, I think the larger point of constantly having to evolve the data sets, I think that is very well taken. And in fact, this is probably going to be even more important as we look into this code that is generated from large language models, because the large language models are already trained on a lot of the code data. So this data pollution is an issue, and in fact, even in the work that we have done recently for repair of code from large language models, we curate the data set very carefully so that it was never seen by the large language model. So this is will continue to be an important issue, particularly in the era of LLMs. Yeah, I just wanted to add.
Yeah, of course.
I think in the interest of time, to getting to the reception on time, we'll go ahead and stop now and thank the speakers again for a wonderful, and congratulations.
Thank you. Please come to ICSE 2023 in December in San Francisco.